Hello, everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much, much more. My name is Saba, and today we are covering something that I have hinted long ago regarding potential distribution functions to model stock returns. We have already discussed that stock returns on real-world financial markets are sometimes deviating quite far from the normality assumption that is the underlying assumption of most simple models in finance and economics. So the natural question to ask would be, is there anything that can be better to understand what are the stock return dynamics, how they are distributed? What is the likelihood of stock returns to deviate far away from the mean? Well, to answer this question, I will be covering some of the most famous non-normal distribution functions that can guide you in your analysis of the stock market. Just as usual, I have the data on 5 years of the dynamics of S&P 500. So from the end of 2014 all the way until the end of 2019. And today, we're going to investigate something called the hyperbolic secant distribution, or the hypersecant distribution for short. Well, the name might sound overly complicated, but bear with me, I will explain it in very simple terms. First of all, regardless, we need to, as usual, calculate the daily returns for S&P 500. So the price today divided by the price yesterday minus 1, and bottom right click it all the way down. Then we would need to rank the returns and present them from lowest to highest, so that we could plot the empirical and the theoretical distribution functions and compare them and assess the goodness of fit. Well, we move from 1 to all the way down to 1,258, as usual, and then we need to figure out the respective returns. So the first smallest, the second smallest, and so on. So the array is the array of returns, naturally. We'll lock that, and we want the first smallest return here, second smallest return here, and so on and so forth. So we basically just rank them from bottom to top, as usual. Now, we can figure out the parameters of our hyperbolic secant distribution and what is the logic mathematically of this function. So here is the distribution function, the cumulative distribution function, expressed mathematically. First of all, just abstracting from the particular distribution function we are investigating today, the cumulative distribution function, essentially, is the proportion of the observations that are equal to or lower than the particular value you encounter. So, naturally, as it represents the probability, essentially, this function should be bound by 0 from the bottom and 1 from the top. And there are a bunch of various mathematical functions that have this bounded property and that you can use to suggest your own probability distribution function that would satisfy those criteria. We all know that the arctangent function is a bound function. It represents value from minus pi over 2 to pi over 2 that gives the value of the tangent function of x, so the argument of the arctangent function. So for example, the arctangent of 1 would be pi over 4, because pi over 4 is the number from minus pi over half to pi over half that gives you the value of the tangent equal to 1. So if we multiply the arctangent of any number by 2 over pi, as we do over here, then instead of getting a number from minus pi over 2 to pi over 2, we would get a number from minus 1 to 1, which is already promising, but not precisely what we want. We want a function that, for any number plugged into it, gives the number from 0 to 1, remember? So here we solve and account for this fact by plugging in not the value of x adjusted to potential, not just the value of x adjusted to particular mean and standard deviation, but actually the exponent of it. What it gives us, essentially, is, as the exponent function is bounded by 0 and plus infinity, then the arctangent of this function, in turn, would be not from minus pi over 2 to pi over 2, but from 0 to pi over 2, as this is bounded by 0 at the bottom. So that would mean that we have actually satisfied the logic of the probability distribution function, as this fluctuates from 0 to 1 for any imaginable value of x. So what we should do now is just figure out the mean and standard deviation given our data, and try to assess how well does the hypersecant distribution fit our real-world data. So the mean is just the average of the returns, and the standard deviation, again, can be calculated using standard deviation for the sample. So a mean daily return of 0.04%, a daily standard deviation of 0.85%. So now, let's figure out the empirical cumulative distribution function. Well, just as usual, we just need to divide the rank by the total number of observations, so 1,258. So now, let's just fit both the normal distribution and the hypersecant distribution onto this real-world data and see which of the distributions gives us a better fit. Well, we have already fitted a bunch of normal distributions to real-world data, so just to recap, norm dist, the x is the rank return, the mean we already know, that's 0.04, and we need to log that, and standard deviation is 0.85%, and we need to log it as well. And again, we need the cumulative distribution function, not the probability density function, so we plug in 1 over here. And that will give us the normal cumulative distribution function. What about the hypersecant cumulative distribution function? Well, for that, we'll just need to convert this formula into the Excel language. So, 2 over pi, and to get pi in Excel, you just need to type in pi and then input empty parentheses. 2 over pi times the arctangent, so a tan, of the exponent of pi divided by 2 times scaled rank return. So basically a z-stat, if I'm entirely honest with you. So the z-stat would be the rank return minus the average and divided by the standard deviation. And we close a bunch of parentheses, enforce the formula, and bottom right click it all the way down. We see that we can already observe it from the left tail, basically, that the hypersecant distribution assigns a much higher likelihood to the extreme events, like a return of minus 4.1% in a single day, than the normal distribution does. Given the normal distribution, the probability of returns being minus 4.1% or lower is negligible, while for the real-world data is still around 0.1%. For the hypersecant distribution, it's uh, significantly lower than 0.08% that we observe in the real life, but still not as bad as straight 0% given by the normal distribution. If we observe that graphically, we can see that those distribution functions fit the empirical data differently. The empirical distribution is this rough blue line over here, and we can see how fat the tail is over here on the left-hand side and here on the right-hand side. The normal distribution completely disregards this feature and has a very slim, very thin tail, while the hypersecant distribution, which is the gray line over here, is somewhere in the middle. So it fits the data substantially better than the normal distribution, but is still not the best that we can do. So, just to recap, the hypersecant distribution utilizes the logic of the arctangent function to convert it into a plausible distribution function. What is important to understand about the hyperbolic secant distribution is that it has fatter tails than the normal distribution. As we all know, the kurtosis of the normal distribution is 0, while the kurtosis of the hypersecant distribution is actually 2. So a good idea would be to assess the kurtosis of the empirical distribution that you are having in your hands, and if it's reasonably close to 2, then the hypersecant distribution might be what you're looking for. It is always reasonable to check a number of different distributions and pick what is the best fit for your data. In our case, we see that hypersecant does a decent job, better than normal at least, but not the best. What would be the best? Well, that would be a subject of our next video. As for now, please leave a like under this video if you found it helpful. Suggest any future topics on videos in business economics and finance in the comments below. Don't forget to subscribe to our channel and stay tuned. Thank you very much.